In modern data engineering, the deepest inefficiencies come down to physics. We are forcing massive volumes of data to travel across slow, external boundaries. Look at this standard monolithic cloud architecture. We see a centralized compute cluster attempting to pull data from heavily distributed application servers. To bridge that gap, engineering teams build complex, highly fragile ETL pipelines. As the data moves through these pipes, two things happen. Packets hit serialization bottlenecks as they are converted for transit, and egress fees accumulate at every network exit point. You are paying for the privilege of moving your own data. Compounding the problem, the centralized cluster at the end of the pipe is highly over-provisioned. You rent expensive, heavy-duty compute to handle multi-terabyte aggregations, but end up burning that same expensive compute on trivial filters and basic transformations. A counter-architecture has emerged to solve this, known as the modern Duck Stack. It consists of three tightly integrated components: DuckDB, the execution engine, Duck Lake, the catalog layer, and MotherDuck, the serverless cloud orchestrator. The thesis behind this stack reverses the standard model. Instead of migrating data into a monolithic vendor environment, you bring the compute directly to the data. You accomplish this by embedding the analytical engine natively inside the environments where your application logic already lives. That execution tier spans an incredibly broad spectrum, operating on edge devices like Raspberry Pis, directly inside web browsers, and scaling all the way up to multi-petabyte cloud object storage. By reversing the data-to-compute flow, the architecture addresses the network I/O bottlenecks inherent in traditional pipelines. The data stays put, the queries travel. Let's examine the mechanics, starting at the smallest execution unit. This diagram represents a single local in-process memory space, like a back-end Python or Rust environment. Notice how the DuckDB engine instantiates natively inside this boundary as a zero-dependency process. It operates strictly as an in-process engine. There is no standalone database server, no daemon, and no socket connection required. Because it embeds inside the host language, it relies on an extensive API client layer. This covers primary core clients like Python, Rust, Go, and C, secondary clients like C++ and C#, and a wide array of community-maintained drivers. Historically, passing data between applications and databases introduced extreme latency through constant serialization. DuckDB bypasses this entirely using Apache Arrow's zero-copy memory mechanics. Pointers map directly between a client data frame, such as polars or pandas, and the DuckDB engine. The data payload is never duplicated. By sharing the same physical memory space, client data structures exchange millions of rows with the query engine instantaneously. The ultimate test of this client portability is the WebAssembly, or WASM, execution tier. By compiling its C-based core to WebAssembly, the engine executes the exact same vectorized SQL logic entirely natively, right inside a sandboxed web browser, with zero back-end installation. Eliminating inter-process communication and serialization overhead shifts analytical queries from a network-bound task waiting on I/O to a purely CPU-bound task executing as fast as the local processor allows. When we move outward from volatile memory to persistent storage, the architecture maintains this strict principle of interoperability. For decades, data systems demanded that you load your information into their proprietary, engine-specific storage formats before you could query it. DuckDB removes that ingestion step. This expanded diagram shows the local engine reading straight from standard open formats on disk, mapping direct read pointers to raw Apache Parquet, Icebird, and JSON files. The same zero-copy read mechanics we saw in memory are applied to these persistent files. The engine scans the data where it rests. This solves a dilemma with live operational data. Normally, you build brittle ETL jobs to extract data from production databases into a warehouse. Instead, DuckDB utilizes direct database attach. We see a connection bypassing the traditional ETL pipeline, linking directly to external PostgreSQL and MySQL nodes. Your analytical SQL queries execute natively against those remote relational databases in real time. By treating both standard file formats and live operational databases as immediately queryable sources, you eradicate the need for intermediate CSV dumps, duplicate storage, and fragile engineering pipelines. Of course, in-process local execution has physical limits. A laptop processor cannot churn through a 100-terabyte aggregation on its own. Modern enterprises store data at that scale on low-cost object storage platforms like AWS S3 and Cloudflare R2, which serve as the foundational data lake. To bridge this gap, the architecture expands to the cloud. This diagram introduces Duck Lake, a catalog layer sitting directly over those object storage buckets, providing sub-10 millisecond metadata lookups. Duck Lake organizes raw object storage into an open lakehouse format, delivering multi-table ACID transactions without a heavyweight warehouse engine. When you need compute at this scale, the Signal component comes online. Serverless MotherDuck compute nodes dynamically spin up, physically co-located right next to those object storage buckets. Together, they create a hybrid cloud execution model. Imagine executing a massive query directly from a Python script on your laptop. Behind the scenes, MotherDuck dynamically splits the query's abstract syntax tree. The execution plan physically divides. A lightweight where clause routes to your local machine, while an intensive group by routes to cloud nodes. The local in-process instance handles the immediate low-memory work, applying simple filters and localized joins. Meanwhile, the heavy lifting automatically offloads to the serverless cloud compute that sits safely adjacent to your data lake. This dynamic tree splitting achieves zero egress cloud processing. The heaviest data movement remains entirely within the cloud provider's internal network, while only the final, aggregated results are pushed down to the client, delivering sub-second performance. This embedded model meets the specialized requirements of modern machine learning and AI engineering. Because the engine relies on a modular architecture, its extensions function portably across every execution environment we've discussed. Look at this SQL script. By loading the VSS extension, the engine operates as a native vector store. It allows you to incorporate k-nearest neighbor searches and cosine similarity calculations directly into standard analytical SQL syntax. At the cloud layer, MotherDuck provides built-in Model Context Protocol servers. This allows large language models and AI agents to connect directly to the engine and query structured underlying datasets using natural language. Within deep learning pipelines, the engine operates seamlessly alongside specialized AI tensor and array stores, like XAR, TileDB, or DeepLake. DuckDB handles the complex, structured metadata queries, while the tensor stores simultaneously stream massive multidimensional array regions straight into PyTorch and TensorFlow data loaders. Executing vector mathematics and metadata retrieval natively alongside standard SQL removes the architectural burden of deploying and maintaining a standalone dedicated vector database. Zooming out, we can see the entire DuckStack ecosystem. This map connects everything from IoT microcontrollers and browser WebAssembly layers to back-end Rust microservices and serverless MotherDuck cloud instances. A single unified thread binds all these tiers together, executing the exact same SQL dialect, sharing the identical .duckdb storage format, and supporting the same portable extensions. This model provides a functional alternative to the centralized, monolithic data warehouse. It treats analytical compute as a lightweight, embeddable primitive, a tool deployed directly to the point of need. By pairing zero-copy memory transfers with direct access to open file formats, you eliminate the friction of data movement. The financial and operational victories are immediate. Network egress costs drop to zero, and the maintenance overhead of fragile, intermediate ETL pipelines disappears. By deploying compute directly to the data, these architectures reduce the need for shipping raw bytes across expensive network boundaries.